Hello, my name is Ayan. I'm a PhD student at SketchX Lab, University of Surrey. The paper I shall present is titled Pixelor, a competitive sketching AI agent, so you think you can sketch. In this paper, we introduce a sketching AI agent competitive to humans in the game of Pictionary. Pictionary is a popular and fun drawing game played by many all over the world. The rules of Pictionary are quite simple. A concept is given to two teams of players. Each team consists of two players, a drawer and a judge. The drawer tries to draw the given concept in a way that the judge from the same team recognizes it as soon as possible. The team whose judge first guesses the concept correctly wins. Our goal is to create an AI agent that can play and win against humans in this game. There is a problem with machines playing the game in the traditional way. Machines are physically and computationally faster, and hence they have an unfair advantage against humans. So we restrict the game to be played in a pixel synchronous way. That is, human and AI will draw the same amount of ink at the same time. Here we show a demo of our AI agent playing against human player. The human player draws the concept on the left canvas and the AI agent on the right. Below the canvas, we see the confidence of recognition over time for both players. The game is rather straightforward. It requires drawing the sketch with as little amount of ink as possible. But that's not enough, as the judge needs to guess the concept correctly as well. The drawer needs to draw the salient part of the concept first. We show an example of a cat. Drawing the face and eyes of the cat is not a good idea, as it's not a clear indication of a cat. However, drawing its pointy ears first is a much better strategy. Now we provide a key insight into the space of all strategies. The figure shown here is a plot of correct recognition score versus the completion rate of the sketch. The recognition score is computed using a pre-trained sketch classifier trained on a fixed set of sketch categories. The curve has a nature of asymptoting towards 1 as the completion rate goes to 100%. Casually drawn sketches, which are not drawn according to the rules of Pictionary, has a rather small hump at the beginning as they are not recognized easily. Sketches drawn with early recognizability in mind has a bulge at the early values of completion rate. Our goal would be to find a way to convert the dashed curve to the solid one above it. The problem can be solved in multiple ways. We simplify the problem in terms of strokes. A stroke is a continuous set of ink points drawn without lifting the pen. We consider strokes to be non-decomposable units of a sketch. The following example shows few strokes that make up a sketch. Our overall pipeline is two-stage. First, we have a module that reorders the strokes of a given sketch in a way that makes a better, in most cases, an optimal strategy for Pictionary. This module is independently trained with a loss function. We infer the optimal strategies for each sketch in the dataset by means of executing inference on this module. The reordered data is then used by our generative model to be able to generate novel sketches with optimal strategy. We now dig deeper into our first module. Before that, we would like to introduce the dataset we used for our experimentation. We use the largest freehand doodling dataset available, namely QuickDraw. A good reason for using this dataset is the stroke level segmentations are available as a part of this dataset. We used 20 categories for our experiments, although it can be extended to the others. The stroke sorting module could be as simple as an exhaustive search over the space of all strategies given a sketch. A strategy is basically one specific permutation of all the strokes. We can iteratively find out all possible combinations exhaustively and figure out which one has a better early recognizability characteristics. But the problem is, we are talking about a search in a combinatorially large search space. A sketch with n stroke requires, at max, factorial n classifier evaluations to determine the optimal strategy. We took a different approach. We use neural sort, a computationally tractable way to search in a combinatorially large search space. The module takes a given set of strokes from a sketch and produces the optimal permutation by means of inference. We will understand the concept of neural sorting. Traditional sorting is a well-known algorithm that permutes a given set of objects according to some predicate. However, it is non-differentiable, hence unsuitable for deep learning applications. Neural sort is a differentiable version of the traditional sorting operator. Here we show a brief view of the full architecture of the sorting module. We start with the set of vectorized strokes from our dataset. We then rasterize them by drawing them on a fixed size canvas. We extracted a 512-dimensional feature vector from each stroke and also from the entire sketch. We concatenate each stroke embedding with the global embedding of the sketch. These augmented stroke embeddings are then passed through a simple MLP to compute a score of relevance. The scores are just one real number that indicates how important that specific stroke is in the context of the whole sketch. Here is the core part. The neural sorting module permutes the strokes according to the relevance scores while still keeping the pipeline differentiable. A perceptual loss is computed with the permuted strokes. We cumulate the strokes from beginning towards the end, and each cumulative sketch is passed through a classifier loss. The loss is used for training the whole system with backpropagation. We will now briefly describe the classifier we used in the sorting module. SketchNet is a popular CNN-based classifier designed specifically for rasterized sketches. It has shown promising performance on TU Berlin and also on QuickDraw. Here we show some quantitative results justifying the effectiveness of our approach. The following is the early recognizability curve averaged over all categories. We also define the metric ERE, or the early recognition efficacy, as the area under the curves. A high ERE is an indication of a good strategy. The original sketch in QuickDraw has an average ERE of 0.612, which is not quite good for being a good Pictionary player. The sketches reordered using neural sort has a much better ERE of 0.715. We also evaluate two different ordering strategy, exhaustive search and greedy search. Please refer to the paper for details. We now move into our next stage, the generative model. First, we introduce the traditional sketch generative models. SketchRNN is a state-of-the-art model for vectorized sketch generation. It uses a popular RNN-based sequence-to-sequence encoder-decoder architecture. It is trained with a standard log likelihood loss and a VAE-style KL divergence loss for learning a smooth latent space. It encodes the sequence of waypoints via its RNN-based encoder, generates the parameters of a latent distribution, samples from it, and decodes with another RNN-based decoder. Despite showing promising performance, this approach does have some drawbacks. It cannot handle long sequences and also fails to encode necessary contextual information. We found traditional SketchRNN model suboptimal for our application. Experiments show that drawing strategies leading to early recognition have multiple modes. Here we can see the sketch has two optimal strategies. To confirm this, we also plot the low-dimensional version of sketch embeddings for normal sketches and sketches with high ERE. We propose an improved generative model, which we call Pixelor. Essentially, it's a sequence-to-sequence Wasserstein autoencoder. We use transformer as encoder to alleviate RNN's long-term dependency problem and also to better capture contextual information. We use Wasserstein distance instead of log likelihood to leverage the presence of multiple modes in optimal drawing strategies. We also use MMD instead of KL divergence to match the latent distribution to a prior. We provide quantitative information that our generative model can better handle multimodal sketches. The table shows ERE values and FID scores of different settings. Please remember that ERE is a measure of early recognizability of a strategy. Higher is better. And FID is a measure of the quality of generated samples. Lower is better. We conduct a human study to validate our hypotheses. We created an online interface to conduct the human study. we let participants act both as drawer and the judge in a Pictionary-like game. In the drawing phase, participants had to draw a given concept with a good strategy. In the judging phase, one sketch is shown at a time, which could be from either of Pixelor, QuickDraw, or other participants. We collected the sketches drawn by participants under our study. We call it the slow sketch dataset. It is comprised of 12 participants, approximately 1700 sketches drawn over 7 attempts for each participant. We show few samples from slow sketch. We present the results of the Pictionary game under an AI judge. The AI judge is a pre-trained SketchNet classifier as described earlier. The sketches from the slow sketch is recognized by AI at 33% completion rate, and Pixelor sketches are at 17%. Clearly, Pixelor has an edge over humans. The result is rather expected as the classifier is well aware of the sketch distribution of Pixelor. The early recognizability curves show that the slow sketch data is not recognized properly even till full completion. We used the judging interface to gather data about human judging. Human participants were presented with one sketch. They can unveil the sketch increasingly at 5% interval, and they can put a label at each interval. We record each label and its corresponding completion percentage. Human sketches are recognized at 33% completion rate. Pixelor sketches are at 31%. Of course, the lower is better. The bar chart shows a category-wise division of the winning rate. The y-axis is the completion rate of the sketch when the correct guess was made. The categories in which Pixelor wins are highlighted in green. We end this presentation with some final remarks. Here we discuss some failure cases for our agent. Since our solution is based on generative models, it is prone to failure. Studying human study results, we noticed that our Pixelor fails in the game against humans when the generative model fails to generate plausible sketches. We noticed that Pixelor often fails to generate repetitive patterns. This work shows the technical details wrapped in a fun game. But more applications are possible, like assisting in child development, improving human drawing ability, or studying human cognition process. Also, we noticed that our participants developing better Pictionary skills over attempts. Thank you for listening. Please visit the project page for more information.